The octopus circuit is a classic way to test components using an oscilloscope. It consists of a transformer that creates an AC signal 50 or 60 Hz, depending on where you are in the world, and applies it to the device under test. The voltage applied is shown on the horizontal input, and the current is shown on the vertical input. This way, the voltage versus current plot can be drawn, and you can understand what's going on by looking at that curve, as each component has a fairly unique signature. Now, in this video, we are going to update this circuit for use with a Picoscope 2000 series oscilloscopes. It helps a lot that 2000 series Picoscopes have an arbitrary wave generator, so we don't even need any transformers. We don't need a connection to the main voltage at all, because all we need is the output of our AWG, and thus the circuit becomes extremely simple. What we have is that we have a arbitrary wave generator of the Picoscope, and if you recall, it's plus minus 2 volts applied through a 600 ohm resistor, and then it will go to 470 ohm resistor that is connected to channel A and channel B, and then the lead goes to the device under test. And here I just use the headers so that different types of components can be connected easily. So we will have voltage on channel A, and the current can be deduced by the voltage drop across this resistor. Sounds simple, right? And it is very simple. If you solder it in, it's going to be pretty trivial. I have a cable coming from a AWG. I have a BNC connector feeding the signal into this header, 470 ohm resistor, some other headers, and this is it. So the next step is to set up the Picoscope software to interpret the signals correctly. And for that, we need to do some math, because we need to figure out the voltage drop across this resistor. And this is going to be the next slide, where we will go into the math channel wizard and set up the following function. We have the voltage drop as channel B minus channel A. We need to multiply by 1000 to get the value in milliamps, and then we need to divide by the value of the resistor, which is 470 ohms. And then we are going to name that math channel, let's say OctoPicous current. Have a unique color for it, let's say black, and specify that its values are in milliamps. And this is about it. Now we have the math channel in the library, and we can use it anytime we want. Now that we set up the math channel, we need to go ahead and switch the Picoscope into the XY mode. So if we already have something connected, we might already see some waveforms jumping around, but we need to go to the XY mode by going into Views, Add View, XY, and then we need to select channels A as our X-axis and OctoPicous current as our Y-axis. We do not need channel B to be displayed on this graph at all. And if we do that, we are going to get something interesting. Here is where there is nothing connected at all, so it's an open circuit. And what do we see? We have a voltage applied and absolutely no current. It does sound like an open circuit, doesn't it? But now let's talk about the settings for the channels and for the AWG. So for channel A and channel B, I'm going to be using plus minus 2 volts, and I found that to get smoother curves, it helps to use resolution enhancement of 11 bits on both channels. By the way, if you are using this option, make sure that you have the same resolution enhancement on both channels. If you're using, let's say, 9 bits here and 11 bits here, that's not going to work very well. And for the AWG, I'm using a sine wave, 100 Hz, and with the amplitude 1.97 volts. Why 1.97 and not 2 is because I don't want to sometimes have the channel overrange issues, which would result in undesired artifacts such as clipping. So I use amplitude that's a little bit lower than 2 volts, and it seems like 1.97 works fine. Now for 100 Hz signal, any time base between 1 millisecond per division to 5 millisecond per division works fine. I just chose 5 millisecond per division because it gives me a slightly smoother signal. But you can definitely play with this time base, and you can play with resolution enhancement numbers until you get a picture that you are most comfortable with. Okay, then we're going ahead. Let's now try, instead of an open circuit, a short circuit, which is obviously just a jumper being inserted into the headers. Well, what we're going to see, well, voltage is going to be 0 because it is a short circuit, and the current will change from minimum to maximum value, and thus we'll have a vertical line. No surprises there. Now, if you go and try a resistor, we are going to get something in between the horizontal and vertical lines. So here, for example, I have a potentiometer that is set to 1000 ohms, and we expect a sloped line, and indeed, this is exactly what we get. We get a straight line that goes 1.8 milliamps over the range of 1.8 volts, confirming that is a 1 kilo ohm. If we use a resistor with a lower value, it's going to go closer to the vertical line, so its slope is going to be steeper. Here I'm using a 100 ohm resistor instead of 1000 ohms, and the picture I get is indeed a steeper slope. We cover 300 millivolts in 3.3 milliamps, and this is approximately what you expect from a 100 ohm resistor. But now let's try something more exciting. Here is a 1 microfarad capacitor, and a capacitor has all the special properties that when you start charging it up, the current is maximum, but the voltage is not, and when it's almost charged up, the voltage is maximum, but the current almost stops. And thus, when we connect it, we are going to see an ellipse. What if we reduce the capacitance and instead put in a 0.1 microfarad capacitor? Is the ellipse going to be stretched out more or less? If you need, you can pause the video for a little while. Well, a smaller capacitor doesn't allow the sine wave of 100 Hz to go through it as easily as if the capacitor is a larger value, and in scientific terms it's called an increased impedance. And so we will see smaller currents going through the capacitor, and thus the ellipse is going to be stretched out more. And this is exactly what we are going to observe. Now let's proceed to semiconductors, and let's stick in a diode. And a diode conducts in one way and doesn't conduct in another way. And so we are going to see an asymmetric picture. And this is how it looks like. At about 0.6 volts, the diode conducts a lot, and we see almost a vertical slope in the curve. Okay, so let's go further to something even more exciting. This is a relay with its coil that has a built-in diode in it. So we are going to expect to see some inductance, some resistance, and even some diode action. So let's go and see what we see on the Picoscope. And here it is. It has a slope which is caused by the resistance of the coil. It has an elliptical shape because of the inductance, and it has a wiggle in the left lower corner because of the diode action kicking in. Pretty cool, eh? But now we are going to make the experiment even more fun, because what we are going to do, we are going to take this coil and get a magnet that is on the end of the screwdriver and touch the coil. And you're going to tell me whether this is going to increase the inductance or decrease the inductance. So, the inductance, more or less? More or less? Well, if you need to think about it, pause the video now. And this is what we get. The ellipse is more stretched out. It means that the inductance got reduced. And a typical explanation for that is that when you get the magnet close to the core of the coil, it saturates it with magnetic field. And so it's harder for the magnetic field to go up and down. And thus, it's not as effective anymore, and the inductance of the coil is reduced. And we see that on the Picoscope loud and clear. I think it's pretty nice. And well, this is it for the component tester using a Picoscope. It requires only a few components, basically just resistor and connectors and some headers, and that's it. And so you can try to make it yourself and play with it. It's gonna be fun.